First, we will cover the concept of software 2.0, coined by Andrej Karpathy. Out of all the benefits of studying AI, I believe that the software 2 mental model is the most impactful. We will explain how it works and how it should change your worldview, even outside the realms of software development. Next, I will cover my reaction to a debate between Eliezer Yudkowsky and Stephen Wolfram. In short, I argue that Yudkowsky is wrong. AI is not going to kill us. I systematically dismantle his worldview, showing not only why his specific arguments are wrong, but also why his entire approach is flawed. Sound interesting? Let's dive in. Andrej Karpathy is one of the GOATs in AI. Previously, he led AI at Tesla and then did a stint at OpenAI, but I think he's probably best known for his AI educational content. During my live stream, I reacted to a talk that he gave in 2018 while he was working at Tesla about software 2.0. Before explaining what that means, let's first talk about software 1.0. In other words, traditional software. Software 1.0 is built by decomposition. In order to build traditional software, every instruction must be handwritten by a human. The problem needs to be completely understood by one person or a group of people in order to build it. AI used to be built with software 1.0 techniques. For example, early self-driving cars had edge detection technology that allowed them to stay within the lane. Here's an example from the 80s.
Video cameras provide color and intensity images for scene interpretation. Road edges, for example, are analyzed through intensity, texture, and color segmentation. A Blackboard computer architecture integrates the distributed processes that sense, map, plan, and drive.
However, this does not scale well. Some problems are just too difficult. For example, if you wanted to build an AI that detects if there's a cat in an image, it would not be well suited to a software 1.0 approach. Look at the incredible variation between these images of cats. But what is fundamentally different about detecting a cat and staying inside lane lines? It comes down to complexity. Distinguishing between cats and other animals is a more complex task than simply following the lane. It's easy to write the explicit logic for keeping a distance between two sides of the lane. Whereas specifying exact instructions for a computer to identify what a cat is very complex. And so we get this idea of program complexity. This circle represents all possible computer software. A single point on this circle represents a single piece of software, such as the one that you're using to consume this content right now. Software 1.0 is simple and therefore occupies space toward the center of the circle. Very simple intro to computer science programs like Hello World would be near the very center, whereas complex software like databases or operating systems or compilers would be further out, but still relatively close to the center. Software 1.0 can get so complex that you need entire teams or companies to maintain them. Complex programs like ChatGPT or Tesla Autopilot would be much further out towards the perimeter of the circle. Since there's effectively no number of people or no amount of resources that you could throw together to build these programs by hand, we need a different approach. They're just too complex. And that different approach is software 2.0. Unlike software 1.0, which is built manually by decomposing the problem and hand coding the solutions, software 2.0 automates the process of building software through optimization. The software 2.0 process searches for the best solution, as you can see in the picture. Before training, the neural network is completely ineffective. But throughout the training process, it learns how to do the job effectively, hence the term machine learning. Training is an iterative process where the neural network adjusts after processing new data. If it makes a mistake, it will learn a lesson from that mistake so that it is less likely to make a mistake like that in the future. This is a slow and grueling way to make software. It involves many iterations that only improve the neural network's performance by a tiny amount each time. But luckily, we can combine many computers to speed it up by teaching it many lessons in parallel. So, after an astronomically large number of iterations, teaching it from an unfathomably large corpus of data, all of these micro improvements add up to create software that can solve the problem it was being trained for. Referring back to this picture, as you can see, the software started off at a given point and was adjusted over time through many training iterations until the optimization process found a good version of the software. Specifically, the term optimization is used because you are trying to find software that makes the fewest possible mistakes. In other words, the error is minimized. So if you're looking at a curve, be it in 2D, 3D, or higher dimensions, you will come across points that you can say that's a maximum point and a minimum point. And both a maximum point and a minimum point can also be called an optimum point. And so optimization is when you move something towards an optimum, meaning a highest or lowest value. Here are some visualizations to show how you might conceptualize an AI training a neural network. Slowly moving the error to a lower and lower value, which means that the neural network will be able to make predictions more accurately. If you want a more in-depth and technical exploration of neural networks and gradient descent, check out my video diving into AI. So looking at the long arc of AI history, not only has software 2.0 become the key to success at Tesla, it exposes a powerful roadmap for how humans can build things never before possible. The less code that humans write, the better. The more that computers can iterate on large data sets, the better the results. This is why over time, less and less of the autopilot software at Tesla is written by humans. The AI is increasingly being trained end to end, and it's getting much better results. Now that we've covered software 2.0, I want to make a case for you that this idea can be applied even outside the realm of AI and software. I've done a good amount of work relating this to crypto, but I don't want to get lost in the details of that. I think I can present to you some more straightforward examples for this video. Allow me to draw an analogy. Think about a startup company. What does it take for it to be successful? As Sam Altman points out, iteration speed is the number one predictor of success. Why? Well, let's look back at this software 2.0 graphic. Just like deep learning is searching for a program that minimizes error in the space of all programs, a startup is searching for product market fit in the space of all businesses. In deep learning, compute generally leads to better results because you can run more training iterations and hence search for longer. The same thing applies to startups. You can think of your initial idea as the starting point, and then iteration drives the search process for that optimal business model and org chart. And furthermore, business as a subject is also an optimization problem. Instead of minimizing the error from the loss function as they do in deep learning, businesses attempt to maximize profit in the market. And fundamentally, this is why markets are able to achieve things that central planning cannot. That's why people say, let the market decide. Central planning requires governance through decomposition. And as economists like Hayek and Mises point out, the world is too complex to govern this way. Not only do central planners lack information that is distributed across society, but they also lack the computational power to calculate the optimal allocation of resources.